Today is Professor Lino Reséndis from Mexico that talk Qp-spaces for hyperholomorphic functions in the unit ball of R4. Please, Lino, you may start.
Yes, thank you very much. Can you hear me?
Yes.
Yeah, it's all okay?
Yes,
So,
it's okay.
Okay, so I am very glad. It's a pleasure to be here again. I will start. This is let me see if I control out. I can put a little bit more bigger. Okay, my screen. Okay, so let me see. Okay, the title of the talk for today is Qp-space for hyperholomorphic functions in R4. Okay, and this is the plan for the talk. First, I will give some preliminaries. Then the second point is to define, to introduce different kind of hyperholomorphic function space, like Dirichlet space, Bloch space, and Qp and Qp-space. All these spaces are defined on the unit ball or R4. After we will be some properties of these Qp-spaces, hyperholomorphic Qp-spaces, and then some examples, and finally we give some words about the vanishing space, vanishing space of this kind of spaces, Qp-spaces. Okay, so okay, first of all, we work with the quaternionic set that we denote by H, and is defined as the set of the points in R4. However, we are denoting in the sense of quaternionic sense these quadruple points: x0 plus e x1 plus iota x2 plus k x3. And in that sense, now in the quaternionic set, we have three imaginary units: e, iota, and k. The product of them are equal 1. And we have the following multiplication rules. Okay, e times iota is equal k, iota times k equal e, and k times e equal iota. And this is anti-commutative structure. And then we denote the unit ball of in the quaternionic space by B. And the modulus is less than 1 in the sense of R4. And S denotes the boundary of the unit ball. Sorry, the unit ball. Oh, sorry. Okay, and also we identify, as I saw, the quaternionic space with R4. Okay, using this natural embedding. Okay, there is well known this algebra of quaternionic numbers is very well known. Now we introduce these two Cauchy operators, D and the bar, and they are defined in this form. D is the partial with respect to x0 plus E, the partial with respect to the first variable, the second variable, and iota, the partial of x2, and finally, k times the partial of x3. And in analogous form, we define the bar operator, and we conjugate the imaginary part of the operator D. Okay. Then this is the first definition. If we consider some function defined from the unit ball to the quaternion, we'd say that this right hyperholomorphic function if the action of f D is acting from the right to F. If the action of df is equal to 0, then we say that F is a right hyperholomorphic function. Also, we will consider for each A point in the unit ball the following Möbius transformation is given by this formula, phi sub A, because depends of the A, from the unit ball to the unit ball, and is given in this form. Okay, these are, we are considering here A and X as quaternionic numbers. For this reason, we can write in this form, this algebraic form, this Möbius transformation. Okay. Now, we define the Dirichlet space of hyperholomorphic of the right in the right model of all hyperholomorphic functions, and the condition is that if we integrate in the unit volt the modulus of the d bar f, and then this is finite, then we say that D belongs to the Dirichlet space. And also we introduce the Bloch space. We introduce the Bloch space within not by B. Also as the set of hyperholomorphic functions defined in the unit ball, such that this quantity is finite. As you see, we are considering here 1 minus modulus of x to power square and then to power squared times modulus of the bar of f. We are imitating the definitions in the very classical sense in the complex analysis. But here we can observe that in the case of the Bloch space, with this first factor, we are keeping control about of the growth of the bar or derivative, hypercomplex derivative of f. If this is finite, then the function belongs to the Bloch space, to the hyperbolic Bloch space. Okay, that's hyperholomorphic Bloch space. Now, follow the following two definitions. We consider in this moment the parameter p between 0 and 2, less strictly than 2. And then the Qp tilde space consists of all hyperholomorphic functions f from the unit ball to the quaternionics, satisfying the following condition. We calculate this integral. We are considering here again the d bar derivative of f modulus to power square, and we consider this wave function. This wave function that we denote by g is okay. First of all, this is the fundamental solution times except for some constant. This is the fundamental solution of the Laplacian in the unit ball of R4. This is the fundamental solution. Then we are composing with some Möbius transformation phi sub A. Then we get this first summand. And after -1. Okay, then G is this function. Okay, and then we consider power P of this function. Please note, observe that if x belongs exactly to the boundary of the unit ball, this is equal to 1. Modulus of phi sub A of x is equal exactly 1. By this reason, then the wave function on the boundary of the unit ball is equal to 0. Okay, and then again we are trying to keep control about the behavior of the growth of the derivative of f, hypercomplex derivative of f, but in some sense, in some average control. Okay, and however, observe also that here there is one problem, because we have some singularity in the point x equal a, the function is equal to 0. Then we have some singularity. Okay. Well, and p is between 0 and 2 because if, for instance, because we want to integrate the weight. Okay. If we put 1 here, then the integration of the weight should be finite. By this reason, p is only between 0 and 2. Now, if we consider p from 0 to infinity, then we can define the following space, Qp be a space that consists of hyperholomorphic functions, again, from the unit ball to quaternionic set, satisfying now this equality. Okay, this okay. As you can see, again, we are trying to keep control about the growth of the d bar derivative of f, and we are trying to keep control using only this factor. Okay, only this factor. Then we have here there is no problem. There is no problem, but however, again, all this quantity is equal to 0 on the boundary of P. In both definitions, you can observe that we are considering the supremum when A runs in all the unit ball. Okay, and then if this supremum is finite, we say that the functions belongs to the Qp tilde space or Qp space. Okay, well, now here in the second definition, of course, it's possible to consider P between 0 until infinity. Now, okay, some properties here. Okay, now it's possible to see very easy that if P is less than Q, then we have these inclusions. Qp space is a subset of Q sub Q space, and also if we choose P equals 0, really, we can prove that the Dirichlet space is a subset of all Qp space. And also the previous expressions defines semi-norms in the space Qp and Qp tilde space. Also, we have the following situation. The Möbius transformation satisfies this equality. Okay, 1 minus power square of phi sub a modulus over 1 minus modulus of x square is equal to this quantity. Okay, here appears a here, and also this is very important. This is the Jacobian, the real Jacobian of the Möbius transformation, but to the power 1 over 4. Okay, also because we need this this kind of set, we define this pseudo hyperbolic bolt that we denote with DAR, and this is the set of points in the unit ball such that the modulus of phi sub x, the Möbius transformation in modulus, is less than R. In fact, this pseudo-hyperbolic ball is an Euclidean ball with center given here. I lost my pointer. Where is my pointer? Okay, here with this center, and with this radius. Okay, and also we define the ball with center 0 and radius R in this form. Okay, now we consider this. We will show that Qp space conforms an infinite unist family between the Dirichlet space and Bloch space. Okay. Sorry. How to move it? Okay, maybe here. Also, it's well known in this theory that if we consider this function psi sub f sub a from the unit ball to the quaternion set, and it's defined in this form. You can see it's a little bit complicated definition because this is the bar of F composed with the Möbius transformation. And also we have this factor that involves the variable W and the point A, okay? But this function is hyperholomorphic, okay? The proof is a little bit, it's not straightforward. It's instead to make a little bit work, but it's a very well-known result. Okay, it is. I should say that in general, first of all, Möbius transformation is not a hyperholomorphic function. First of all, and also it is no. Okay, but the reason this is not so easy to prove, so to have the result. Okay, and now we will prove the following. If P is between 0 and 2, then each Qp tilde space is a subset of the Bloch space. And if P runs from 0 to infinity, then each Qp space is a subset of the Bloch space. Okay, the proof follow the following steps. We can choose one point in the unit ball, a fixed value between 0 and 1, and we consider in this case P between 0 and 2. And we will use, because, okay, I forgot to say the following: each hyperholomorphic function is automatically harmonic function, okay? It's harmonic function. Then, since this function is hyperholomorphic, and this function is hyperholomorphic, okay, and then we have all these functions to the power square is subharmonic function. Then we estimate from the definition of the Qp condition, okay, we estimate. First of all, instead of integrate of the unit ball, then we integrate in this more small set. Then this is immediately, okay. Then here we use the definition of the function g, this wave function. A moment. Down here. Okay, and now we estimate the weight. We make some change of variable here. Okay, we use a change of variable here using the function, the Möbius transformation phi sub a, and by this reason now we have that we integrate over this ball. Okay, here are some estimations making this change of variable. Here, then here appears the Jacobian. Okay, and then we write all this quantity and use some estimations in this form. Okay, in this form, and precisely in this expression appears the function c, the function c. But we know that this function is subharmonic, and then we can estimate this integral. We can get a lower estimate of this integral over this ball. Okay, and then we estimate. We pass first to polar coordinates. Okay, we write in polar coordinates, and then we apply subharmonicity. Okay, because then this part of this integral is greater than its value in the point 0, in the point 0. Okay, and the point 0 is precisely this value. Then we have this estimation, but as you can see here that is the modulus to power 2 of the bar of f, and here is 1 minus modulus of a to the power square to power 4, but it is the definition of the Bloch space. Then if the function belongs to the Qp space, if we consider here supremum, also we can write here supremum, and then this, if this is finite, then this is finite. Okay, Then for this reason, each function in the Qp space belongs to the, each function, sorry, in the Bloch space belongs to the, each function in the Qp space belongs to the Bloch space. And we get similar result. If we use this definition for P between 0 and infinity. We get exactly, not the same estimation, but almost the same expression. Here is the Bloch definition, and here is the Qp definition. Now, okay, now we require the following estimation. It is very easy to calculate this integral. Okay, this is it's true for p greater than 3. Okay, and then the exact value of this integral is this value. Now we have the following proposition. Now we consider some hyperholomorphic function from the unit ball to the quaternions. But we are considering now p greater than 3. Then if we consider a point in the unit ball, and we suppose that F belongs to the Bloch space, then observe that here we have the definition of the Qp space. Here's the definition of Qp space. But now we can estimate this integral in this form, and here appears the definition of the Bloch space. Okay, then we have here that it is finite, then this is finite. Okay, the definition, the estimation is very easy because we are supposing the Bloch condition. We have this estimation because now the hypothesis is that F belongs to the Bloch space. We apply again some change of variable, and then we estimate the definition of the Qp space, because then we can change this first factor by this factor, the estimation of the Bloch norm, between this factor in the denominator. Okay, then we make some transformations here. We use again some change of variable here using the Möbius transformation, and we obtain finalities. That means that if this is finite, then this integral is finite. Okay, and then we have the following result. In general, if p is less than is greater than 3, then exactly all Qp spaces are equal to the Bloch space. Okay, and then in particular, all Qp spaces are equal between them for all Q and P greater than 3. Okay, then we have the following question. We don't know if 3 is the minimum value of Q, such that the Q space is equal to the Bloch space. Okay, we don't know. Maybe 2.5 is the minimum, or maybe I don't know. I don't know. Okay, but we don't know the answer to this question. Now, the next estimation is used to obtain some relation between Qp space and Qp tilde space. Okay, this estimation is in some sense very elementary estimation. However, I will try to explain the sense of this estimation. I don't know how to move this. Maybe here. Okay, we consider p only between 0 and 2, and we consider some fixed number between tau between 0 and 1, and we consider some positive real function defined in this interval, but this function is increasing. Now, observe here that we have this integral HR r to power 3 dr, and here the same limits, the same function HR. However, here, okay, the power of 3 is 3 minus 2p, okay, and then as you can see, you could see, please, you can see here, for instance, p is, for instance, you can choose p very close to number 2, but this reason the exponent, for instance, here is negative, okay. Then we have some, as you can see, there is no exact direct comparison between this integral and this integral, okay. For instance, again, for p close to the number 2, okay, because we have some singularity at the point 0, okay. However, if we suppose that the right integral is supposed finite, even when tau is equal 1, when we put here tau equal 1, then we can compare it. We can compare it in this form, the second integral. Here, this is immediate. However, because my first comments, however, this estimation is not trivial, okay, because the singularity that we have here. However, it's possible to have this estimation. But this reason, this is a very, maybe the proof is not so, it's not difficult to, okay, it's necessary some tricks to estimate this integral, okay, but it's not straightforward. Okay, it's necessary to make some calculation, but this is the main reason, okay, because here we have some singularity the point 0, and here not, okay. However, it's possible to get this this estimation, but please consider that the true hypothesis here is that H is positive increasing function, okay. Here appears the proof. I didn't discuss the proof. In general, this is immediately, okay. There is no problem to estimate the to have here some estimation directly for the powers. The other estimations, for the second estimation, it is necessary to divide this integral in two different integrals. Okay, I will say some words only about these two lines, as you can see. Okay, here we are considering, we consider some point t between 0 and tau over 2. Then we divide this integral in these two integrals first, okay? And after, this is the key point, because h is increasing function, we can put h out using the value h of t, okay? And then we have these two summands, okay? And in fact, the constant, it should be defined in this form. Okay, there is no problem with the existence of this integral because p is never 2, is less than 2. P is less than 2, and then this is a constant that is well defined. There is no problem. Okay, but okay, only these few words about this this proof. Okay, but the key point it will be here. Okay, the proof is here and so on, but I will omit. Okay. Now, this result is used to prove that if we consider p between 0 and 2, then both spaces are the same space, and of course the seminorms are equivalent. Okay. First of all, this inclusion is quite immediate Okay. Now we will consider the opposite inclusion. Then we will consider that F belongs to the Qp space, and then if we consider the definition of the Qp space we have here, and then we change of variable using this change of variable using the Möbius transformation, we get this, and we consider again the other definition of the other space using only this weight function that you can see here, 1 minus modulus square of phi sub a. Okay, and again we use this change of variable. Okay, and then it's possible to write the expression now in this form. And here you can see the main difference between both expressions. This expression doesn't have singularities, okay? But here we have a singularity at the point 0, okay? Then it's necessary to compare these two expressions, okay? Then in order to get this, we consider first the definition here, the first definition, and then we consider first this this estimation. We consider the integral over all the unit ball, and then we remove this ball of radius 1/2. Okay, then it's possible to estimate the denominator here because now it's not 0, and then we can estimate with this number. Okay, and we estimate all the integral again in the full unit ball, and then we have here. Okay, why? The problem is when W is equal to 0. Now, if we consider this ball with radius 1/2, then it's possible to estimate this quantity here between these two numbers. And again, now we change to polar coordinates. Okay, we consider this integral on the ball of radius 1. Okay, we can estimate here. Okay, and we change to polar coordinates. And if we change to the polar coordinates, we get this expression. We get this expression. Okay, we get this expression, as you can see. And here appears precisely this exponent that appears in our previous proposition. Okay, and also we have for the other definition, then we have also this estimation. Okay, and again we get this estimation, and here is the other part, r to power 3, and the same function here. And then it's possible to apply the result of our proposition 3.3, but we use with tau equal 1/2, and we consider this increasing and positive function. Recall that this function is subharmonic. By this reason, the definition of this function now gives us that it's an increasing positive function. And then it's possible to apply our previous result, and then we can estimate. We can estimate the this integral now in the full complete unit ball, and with this integral also in the complete unit ball. But this reason now these two spaces are equal, but only when P is between 0 and less strictly than 2. Okay, then these two spaces are the same. Okay, only some remark here, because if we consider P greater or equal than 1, our weight function is equal to infinity. Okay, and again, we don't know if this inclusion is strict for P between 0 and 2. The supremum when we consider Qp tilde, okay? Because we don't know really how behaves Bloch space, this Qp space with respect to the Bloch space. We know when we consider the Qp space without tilde that if P is greater than 3, there coincides with the Bloch space, but we don't know answer between even the supremum here of these spaces, and also with P greater than 2, between 2 and 3 for the other space. Okay, now, now we will consider the following. We consider now, because now we want to know, to build some kind of examples of these functions. Okay, then we consider some C1 function from some domain in the quaternion space, in the quaternion set, but such that the operator of F is equal to 0, and also the bar operator of F is equal to 0 for all points in the quaternionics, for instance. Okay, then we give F in this form. Okay, we apply both operators, the operator and the bar operator, and we consider that its value is 0. If we add both expressions, then we get that the partial of F with respect to x0, x sub 0 is equal to 0. That is, does not depend of the variable x0. If we suppose additionally that F does not depend of the variable x3, then we obtain these two Cauchy system, Cauchy-Riemann system, okay? Or Cauchy system, okay? We obtain this Cauchy system, and that means that if we define the function h tilde in this form, okay? Then this function satisfies these Cauchy-Riemann equations with these identifications, okay? With these identifications, okay? So, in a similar way, we can have we can get another Cauchy-Riemann equations for this function, tilde, and also we get a similar consequence. If now it's independent of x0, x2, or x0 and x1. Okay, then we can get some examples of this form. Now, in this way, we have proved the next lemma. If we consider a C1 function from the unit ball to the quaternionic numbers, and then we consider the function given in this form, with that satisfies this condition. And then if F is independent of x0 and F is additionally independent of x3, then these two functions are complex analytic as function of these complex variables. Z equal x1 plus E times x2. And then, if R is any function that belongs to the Dirichlet or Bloch space, and F is like our previous lemma, then these functions belongs to the Dirichlet or Bloch space respectively. Okay, because if we apply the bar operator, then the bar operator of F is equal 0. Okay. And here there is another example. If we consider some domain in C, and we consider any analytic functions on this domain, and we make this identification, we identify this quaternionic variable with this complex variable, and then we form this quaternionic function. This quaternionic function, then this quaternionic function satisfies that D applies to F is equal to D bar of F, and both are equal 0. In particular, we can consider this if H is this analytic function for each beta greater than 0, and then we can define F tilde given in this form, where F1 and F2 are, F1 is the imaginary part of H, and F2 is the real part of H. And then this function satisfies again d and d bar of F tilde is equal 0. And then now I think I don't have so much time. Okay, again, if we consider any hyperholomorphic function such that d bar of R is bounded, okay, is bounded, then of course this, because d bar is bounded, then this function belongs to the Dirichlet space. And again, we can consider this function and also belongs to the Dirichlet space. Okay. Another kind of examples can be constructed using some development. This is not exactly power series in the typical sense, and this power is not exactly typical sense of power. However, it's possible to get several examples using this kind of products, developments, and get more additional examples. I will escape this. Maybe I will mention only some properties now. First, that all we have the following. If we consider the classical Qp theory in the analytic case, then we have the following results. If F belongs to the Qp space that is defined in the unit disk, okay, then F belongs to the Qp space if and only if we calculate all this integral and it is finite. In the classical sense, Qp is only the first derivative to power square, modulus to power squared, and the modulus, and we use the typical green function. Okay. However, if we consider, as you can see, if we consider F in the Qp space, then not necessarily every primitive of the d bar of F belongs to the Qp space. Okay, in the classical Qp space, this result is true. If we consider some function in the Qp space, then its primitive belongs to the Qp space, but here not. Okay, F can be Qp space, however, its primitive cannot belong to the Qp space. Okay, here another kind of results. This if we consider some sequence of hyperholomorphic functions that converge uniformly by compact sets, then it limits also its hyperholomorphic function. This is quite a normal result. And now we can introduce this space because our previous space are not complete spaces. Now, but however, we can consider this Qp star space. Okay, here is the definition of our previous spaces in this part, and we are using this part. Okay, this part is some definition of some kind of Bergman space, because here appears directly the function. Okay, and this new space in fact is complete. In fact, is complete. Okay, in this form, this is a subset, of course, of our previous space, but these spaces are complete. These spaces are complete, and of course, it's necessary first to introduce this kind of weighted Bergman space, and these weighted Bergman space are complete. Okay. Well, and then after this space, we can introduce this, and this space are also complete. Okay, so okay, I will escape this. This space is complete. And also to enter this talk, so only some few words about the vanishing space. We say that one function, one hyperholomorphic function, is a vanishing Bloch space if instead of the supremum, now we consider the limit when the modulus of x tends to 1. If the modulus is equal to 0, then we say that f belongs to the vanishing Bloch space. And again, of course, this vanishing Bloch space belongs to the Bloch space. Again, we can also introduce the vanishing space Qp0. Again, consists of hyperholomorphic functions from the unit ball to the quaternionic set. However, now instead to use supremum over E is finite, now the limit when the modulus of A tends to 1, this limit is equal to 0, is equal to 0. Then we say that belongs to the vanishing space. Okay? Here, that means the following. Now, the weight function keep total control about of the growth of the d bar of f in average, of course, because I consider this integral. But now the weight function keeps the control. Okay, it's possible to prove, for instance, that the Dirichlet space is a subset of all these intersections. We can consider the intersection of all vanishing spaces, okay, in the defining unit ball, and the Dirichlet space is a subset of this space. Okay, also from P between 0 and infinity, of course, we have this, we have also this inclusion, and also we can consider all this intersection, of course, is subset of this Bloch space. And we consider this function that is defined in the unit ball. This is the definition of our Qp space. Then this function is continuous in the unit ball, and as a consequence of this fact, we have that the vanishing space is a subset of the usual common Qp space. Okay, and finally, I don't know if I have, okay, that is all. Thank you very much for your attention. Thanks.
Okay, thank you, Professor Lino Reséndis, for your interesting talk.